Hello, everyone. We have a full house and people from California and Long Island and Phoenix. And yeah, that's all the places I can see right now. I'm sure they're from all over. So I am here in Orlando, but I am a lecturer on the live team, I guess it's called now, at Flatiron. And I have been there for about 4 months. Prior to that, I was in academia and consulting and research doing data science and all those things. So today I wanted to kind of give you a little insight into what happens at the Flatiron Data Science Bootcamp. And I have to admit, I try to simplify this model as much as I can so as not to overwhelm anyone. But once we're done, I'll send out the file and you can play with it and do have fun, right? That's what programming and data science is all about. So I'm going to share my screen now. So let's take a look. And can everyone see my screen?
Yep, I see it.
Okay, cool. Yeah, so this is the classification tree model, decision tree model that we're going to build. And I was hoping that it would come in bigger than this because I'm using a extension for the Jupyter notebook that turns your Jupyter notebook into slides, but maybe that is, maybe I probably will be going back and forth between the slide and the notebook just so that I can kind of, let me see if I can blow this up. Yeah, so there we go. That kind of looks better. So yeah, so this is what a classification tree would look like for, in this case, heart disease, right? And so you would, use your data, you would model the data to build one of these trees, and then you would be able to use it to make decisions about patients and their risk for heart disease or whatever disease you're trying to model, right? And so it would use the different features of the patients, age, gender, heart rate, cholesterol, all these things. And so you kind of have, something here where you decide if the patient has heart rate or blood sugar or cholesterol more than a certain value or less than a certain value, and you would keep going like that until you get to the end. And it usually would give you some kind of a value, and some decision trees end with a percentage, but this one is a simpler one. We have a smaller data set. So before we go into the modeling itself, I just wanted to give sort of an overview of what happens at Flatiron in terms of the bootcamp. So we have 5 phases. The first phase is the data engineering, where you learn all about Python and pandas and SQL. You learn how to clean your data, how to manipulate your data, and the fun part of data visualization. You learn all about that in the first phase. And then in the second phase, that's where the statistics come in. Predictive statistics, inferential statistics, learn all about, do you remember your mean and your standard deviation and, all that kind of stuff to help you understand the data a little bit better. Sometimes there is some hypothesis testing that's required, and you get introduced to your first model at this stage, which is the linear regression model. Then, I forgot. So phase 3, and it's off screen right now. So that's where you actually start doing the machine learning building. So you start doing all kinds of building all kinds of models, classification, supervised learning, do k-nearest neighbors and regression trees, logistic regression. You learn to build all these different types of models from your data, how to evaluate it, how to optimize the models, how to test them, how to build pipelines for your models and all that kind of stuff. And then phase 4 is where you get into the advanced topics, right? Time series and clustering, recommendation systems that are so popular now with everyone, because, you know, right now, the thing is what's the movie place? Netflix. They made a claim that their recommendation model earned them something like some ridiculous $100 billion last year or year before. And so now all the companies want to build recommendation models. So that you need data scientists. So there's just like really, you know, the market is wide open as far as data science jobs are concerned. And then finally, it's phase 5 is where you, you know, build your own project. You go and you acquire the data and you build the project that you are, you know, you either have some passion about, or maybe it's related to something that you're already doing. You know, there was one student who was working and was attending Flatiron on a part-time basis, and he was not part of the data science team at his job, but he decided to build a model nonetheless with the data from his company. And his model outperformed the model that had been built by the seasoned experts at his company. And so that was his capstone. And so he was so excited. He couldn't wait to show it to his boss. So he had some of us, the lecturers and instructors, kind of look over it, make sure, you know, everything was, you know, correct for the most part. And he shared it with his boss. And so I'm not sure what happened, but we're thinking that maybe there was some kind of a pay increase or promotion involved. So that's what you would be getting into when you become a student at Flatiron. So today we're going to build the classification tree or the decision tree model. And there are various steps that I will be going through as we build this model. And as I go through the steps, I will try to show you, you know, what the activities that I'm doing and what phase it relates to, right? So, because before you get to the stage of model building, right, you have to develop your Python and your programming competency, and you have to, you know, get a good foundation in statistics and, you know, just understanding what you're doing before you actually get into the model building stage, because there's several steps involved in generating these models and, of course, in optimizing these models. So we want to make sure that there is a good foundation in place at first. And I guess, Jelani, you'll let me know if there are any questions, right?
Yeah, I'm answering a few of them.
Okay, cool, awesome.
In the chat now.
But yeah, if there's any that I can answer, just let me know. Yeah, so we're going to start by importing our data, doing a little bit of data exploration before we actually get into the modeling stage, right, where we you know, do some analytics on our data. So before you do any type of data science, any type of machine learning, it always starts with importing or loading in the model, the modules, I should say, the modules. These are the modules, right? So, you know, Python is the base language. It's the language that is used by most data scientists. But in addition to base Python, we use other modules that help to expedite this whole process of data analysis, right? So we have modules that help with the cleaning and the formatting, and then there are the models that actually do the modules that do the modeling. It's a lot of models. So that's what we're going to do here, right? So we're going to import the modules. So when you get the copy of this file, which I will share with you, you want to make sure that if you want to, you know, compare your results to mine, that you have, you know, all the latest versions of pandas and NumPy and sklearn. So, you know, you're going to have import pandas, matplotlib, Seaborn. Fortunately, all of these are open source, so you don't have to pay for them, which is really good. And these are, I probably have more models more modules than I need right now because I tried to simplify the model, but it doesn't hurt to import the modules into your Python notebook first, right? So once you have imported the modules, now you can import the data. And the data that I'm using is the heart disease data set. This is from UCI Machine Learning Repository, which can be found anywhere on the either UCI's website or Kaggle, or it's a very popular data set that a lot of people use for learning and developing their data science and machine learning skills. So in this data set, we have information about patients, their age, their sex, blood pressure, heart rate, just a whole host of indicators that help us to then make a determination. We also have, of course, the end of their outcome, whether they have heart disease or not. So that's what helps us to be able to make some kind of predictive modeling as far as this condition is concerned. So we use the syntax pd.cv. pd.read.cv. So PD here is for the pandas, right? And this read_CSV is a method of pandas that allows us to import data set into our notebook and import it in such a way that it comes in as a pandas data frame. And these pandas data frames, they are very much like a Excel spreadsheet, SQL table. They look very familiar. So if so I've already typed this in, but if you type the data.head, since I think I have to run my code because I may not have done that. So let me make sure that I run all of this. So usually you see a star here while it's running, and then it changes to a number. And now I can go ahead and I didn't run it because it's blank right there. So I can go ahead and do this to load the data set. So now it's loaded and I have assigned it the name DF, default data frame. I probably could make it something more informative like df.heart or something of that nature, but it's easier just to do DF because I have to keep typing that over and over again. So this is my data set. Once I run this code here, so now we have loaded the data and it has been assigned to the variable name DF, right? So this is another method of the data frame head. And when you call that, it gives you the first 5 rows of your column, of your data set, sorry. 5 is the default. If you wanted to do more than 5, you can change the number in there. But this is what you do. Once you've loaded in your data set, you want to make sure you check it out and see what's happening. So now we see we have the data set, we have some values here, but something's going on because the columns are headings. This is another method, info. So we get all of the information about our data set. We get how many entries, meaning how many rows, 303, and the list of columns. We have 14 columns because it starts at 0. And then we find out that all of the columns are either float or object type, which refers to categorical. This refers to the float is a type of numeric, and object is categorical or string. And so we see what type of data we have. We have 300 entries and each column has 300 entries. So that means we have no missing number. That's something that's really important to our data sets because the machine learning modules that we use, they are very sensitive to inaccuracy, wrong numbers, missing numbers, outliers, and those kinds of things. So those are the things we have to make sure and check before you actually do your modeling. The modeling is usually the last stage. There is a whole lot of data preparation and data wrangling and data cleaning that takes place before you do the model, because you have to do all that. And then, you can use any one of the many modules that will help you to build your data, build your model. So, so in this data set, this is some of the information, and some of it is off screen. So again, I'm going to go down back to my notebook. So we have age, we have sex, we have chest pain, resting heartbeat, cholesterol, fasting blood sugar, and a whole host of other features that we are using. But we noticed that when we looked at the data frame, we only saw numbers, right? So see, these are the things that you have to make sure and check out before you start modeling the data, right? So now we know we have the column names as numbers, but we do have the list of the columns. So now we have to make sure that we add these names to our columns, right? So we are creating a list here. So we're creating the list of columns with this. And then when I run ahead again, we see now that our data frame has the right title for each of the columns. So that's just one of the things that you want to make sure and do. We can look at the type again, and we see the column names now listed, correctly as they should. So this is how our columns look. So now we can do a bunch of things with our data set. So we need to check out and make sure. So we want to build a classification model, and classification models are used for predicting targets or outcomes that are categorical, right? If the outcome is continuous or numeric, then you would use a regression model. You would use a linear regression, or there are other types of regression models that you can use. But if it's a classification model, then the outcome is going to be in categories. And so in this case, our outcome here is HD, right? So that was whether they have heart disease or not. So that is our target. And we have to make sure that that the target is actually, first of all, categorical, like we need it to be, and that there are no missing values, that there are not any kind of outliers or crazy numbers in there. So one of the things that we can do is we can take a look at what is inside of the actual this column, right? So this would be the column here. So we're seeing just few of the numbers here, but we want to know exactly what are all the numbers in there. And this is another method of the data frame, or more specifically of the series, right? So we can select just one column at a time from our data frame. That's the beauty and the versatility of these data frames. So we can select just one column, and then we can take a look at it and see what's in there. So we use the method, the value count. And so this is what we see. So we have 5 values, 0, 1, 2, 3, 4, 5. And so 164 patients or subjects have a heart disease classification as 0. So that means they have no heart disease. And then there are 55 who have 1, 36, and so on, so on. And we don't have all the information specifically about what those different numbers mean in terms of the different types of heart disease, whether it's coronary heart disease or it's myocardial infarction, or what the type of diseases are. And so in this case, I tried to simplified this modeling process right now to keep it within the time limit. And you'll see later where I basically put all of these into one category. So, making no distinction about the type of disease, heart disease, but just that they had heart disease, right? So that was one of the things you can do. So we had the value counts. This is another method that we can apply to our data frame. So we have the data frame here. This is a method, group by, and we can use group by to group the whole data frame by a particular category. and get the mean for each of the values. So in this case, we're grouping by sex. And so we know sex was one of the columns in our data set. And if we ran that, so we get this here. So now we see we have two values for sex, 0 and 1, right? And 1 is usually refers to males, and then 0 refers to the females. So here we can see the average female in this data set is 5.72 years old, young, however you want to look at it. And the average male is 53.83. And you can get all the other measures and see how they compare to each other. So not much difference for the chest pain, the cholesterol. The women have a higher average cholesterol than the men. So you see the 261 and the 239. And then here you have resting heart rate, not much difference, not that. So this one, there's something going on here where the average for men is higher, also for the old peak and slope. And so now we have the average as far as the target is concerned, heart rate. So remember, these are the classifications. So they're basically adding all of this up for each of them and then dividing by the number. And so clearly there is a higher, on average, incidence of heart disease among the men than the women. So these are some of the things that you do before you start building your data, because there's so much insight that can be gained, whether it is understanding the population that you are working with, or maybe you have business data and there might be questions that your manager or your client may want answers to. And so doing this type of preliminary type analysis is what helps you to be able to answer some of these questions. So once we've loaded our data, we've looked at it, we see what's going on here. The next thing would be look for missing values, right? So we want to make sure that there are no missing values. And, in a more involved process, there's several ways to deal with the missing value, because it depends on whether the values are numeric or categorical. It depends on whether the missingness of the values are associated with the outcome or not, or whether there's some correlation between how many values are missing for one group versus the other, right? So if we find out that, say, age category has a lot of missing values, we could, depending on how much of it is missing, we could delete it, or we could impute the mean of all the ages. But if we did some further classification and found out that most of the ages that are missing are from the women because they didn't want to tell their age or something like that, then we would not use the total mean, but more so the mean for the women, because that alone introduces a significant amount of bias. And that's one of the biggest problems in our machine learning data modeling activity, always trying to minimize bias, right? Because when we build these models, the goal is that they should be generalizable. They should be able to be used with a group of people or a data set that it has not seen before. But if there is significant bias in your model, then it would not perform effectively and would essentially generate incorrect and unreliable information. So we want to always make sure that we are minimizing bias. So we have this.
You want to, real quick?
Sure.
There's a question. Would you want to convert this to a binary classification, since we are not concerned with the type of HD? Just true or false?
Yes, exactly. That is very good. That's a great question. Yes. So that is one direction we can go, which is what I will do later, to convert the heart disease to a binary classification, right? So that is something that we can definitely do, and we can use that to build, for example, logistic regression models are based on, especially, of course, binary logistic on binary models. And that is a quick way to go about it if we're not really interested in understanding what type of heart disease is. But sometimes we do want to know what that is, and so we leave it as it is with the many categories. But yeah, very good question. I will turn that target column into a binary soon. All right, any more questions?
Not right now. I think we're good for right now.
Okay, so now you notice when I did n unique, which is another method we can apply to the data frame, the series or the columns of the data frame, it gives you all the unique values. And here we have 0, 3, 2, 1, and question mark. Interestingly, when we looked at the data set here, we noticed that it says no, none, null. So that would imply that there are no missing values, right? But when we dug deeper and we use the n unique, we see that we have question mark in there. And so that is being essentially recognized by our data frame as a value. Of course, it isn't, and it would not, we wouldn't be able to use it in our modeling. So we would have to take care of that. So if we looked at the unique, we saw those values. If we use the same method again, value count, we see we have 4 question marks for the CA category. Similarly, this it has some question marks as well. There are 2. So we want to take care of those missing data, right? So if we notice, we have 2 here and we have 4 here. So if we ran this code, which is essentially telling us we're selecting from the data set all of the rows, right? That's what the loop does. We're selecting the rows where the value is this this question mark. We're doing that for the CA column as well as the SAL column. And if we selected that out, from the data frame, and then we did an LEN, which is a Python built-in method that lets you get the length of anything, length of your string, length of your column, length of your data frame. So essentially it's telling us that we have 6 rows where this question mark, values are concerned. And so we want to make sure that we took care of them. So if we printed it out, these are the 6 rows. Now remember that how many rows did we have in our data set? Who can remember? Let me see, type it in the chat. Yes, that's correct, Ellen, 303. So if we have 6 rows out of 303, what percentage of our entire data set is quote unquote has an error? 2%, that's right. So we could easily just delete that, right? Because the kind of the rule, well, I shouldn't say rule, but the recommendation is that if your missing values or incorrect values are less than 5% of your data set, then it's okay to delete that without any severe consequences as such. So that is exactly what we're going to do, right? So we're going to delete that. Yeah, so this was where I looked at, this is an attribute of the data frame that lets us know how many rows, and here's how many columns, and this is where I did the calculation about the 2%. So now we are going to essentially get rid of those missing values, as it were. So what we're doing here is we are creating a new data frame. So my data frame was DF1. So now we're creating a new data frame. My original was DF, now it's DF1, because I am going to eliminate all of the rows where this question mark is. And so this is the code I'm using. So what I'm saying is return to me all of the rows except That's what this not equal means. The ones where there's a question mark, right? So we run this code, and now if we took if we got a length of our new data frame, it is now 297. So we've effectively gotten rid of those 6 rows. And now if we ran those series methods again, we will see that we got rid of the question marks, right? So that's one of the things that you have to make sure you're doing when you, before you're doing any kind of modeling. Yeah, I sorry I didn't share the notebook, but I will. I promise, Samantha. I know you're eager to code along here with me, but yeah, just try to follow along and try to catch any mistakes. That's the challenge, right? So we have our new data frame that is free of missing values, or so we think. You know, you always want to run these methods, the info and the shape, right? Because it's very informative, and it doesn't just give you information at the start, but as you progress through your modeling activity, if you run into any problems, you have some errors, you can use these methods to kind of help you understand what is going on with your data. So now the next thing that we want to do, just like who was it that asked about the binary condition? Yeah, so the CA is for chest something. Let me go back up here where so the CA is number of major vessels colored by fluoroscopy. Yeah, so that's what the CA is about. We'll probably get rid of that at some point. But someone had said that, asked about converting it to a binary. Right, so that's a great question, Joanne. If it is that there is a higher percentage of missing values, there are several ways that you can deal with the missing values. As I indicated before, you would have to do some preliminary analysis, some bivariate analysis to determine if there's any pattern to the missing values, right? So in machine learning, there are actually different types of missing values. There's missing at random, missing not at random, and missing, I forgot what it's called, missing probably at random. That's not the name. But so there are different levels to the missingness, and as such, based on what category those values are in, you would want to do different things. So in this case, the missing values here were first categorical, right? So then you can't do what you would do with a numeric value. You would have to do some, if it's a numeric value, you could use the mean, right? You could find the average for the entire column and use that to fill in all the blanks. But that is dependent on the fact the value, the distribution of the values have to be normally distributed, right? Because if they're not normally distributed, then the mean is a misguided measure of central tendency. For example, if it were, what do you call it? Like pay data. What is pay data? Income, there we go, that's the word I'm looking for. If it were income data is notoriously skewed, as you can imagine, right? Because you have the majority of people making $50,000, $60,000 a year, and then you'll have the managers and the CEOs making, I don't know, 10 times that much. So if you want to, you would not want to use the mean to substitute for that in the missing values, because that would really just change the whole nature of your variables. Missing completely at random, missing at random, missing not at random. Yes, that is true. Thank you, Bilal, right? These are the 4 types of missing. And so, yeah, you would have to go in and figure out if your missing values fall into any of those categories. And for each of those, then you would have a different approach to filling in those values, right? So if it's here, in this case, it was categorical values that were missing. You could essentially use the mode. In some of the sklearn packages, they have imputers that can automatically do that filling in of the missing values for you, so you don't have to do this. Vin says, are outliers handled the same way as missing values? Not quite. So outliers are a whole different beast, right? Again, it depends on what kind of machine model you're building, because some models are more sensitive to outliers than others, right? So in the case of linear regression, very sensitive to outliers, but some of the classification models, not so much. Then if it's, with the linear regression, if the outlier is, you generate a scatter plot and you have a trend line and the outlier is way out there, but it's still on the trend line, right? So essentially in that case, including the outlier or not does not really change the final regression equation, in terms of the coefficients of the features. So, in that case, you would kind of build a model with the outliers and a model without the outliers, and see how that changes. In other case, depending on how many outliers are then they're not really outliers. They could just be a different classification of the outcome. And so again, that would have to be handled differently. If the outliers are, whether they're in the features or the outcome variable, that's different in terms of whether you do some kind of transformation, because if you're doing a linear regression model, right, you want to make sure that the data is normally distributed. If there are outliers, it's not. There's lots of skews. So you may do a log transformation, and that may take care of the outliers in some cases. And you can run your model and evaluate it and see if that, so you do the modeling pre-transformation, post-transformation. There's a variety of ways that you can think about that. I think outliers are up next. Yeah, I didn't really go into it, although I think I have it labeled here, but yeah, so those are just some of the things that you would be doing. So like, if you were in the boot camp, the second phase when you're doing the statistics and the statistical analysis, that is where you would learn all of the different methods to deal with both the missing values and outliers and all that kind of stuff. So we did. We were going to, yes, take care of our outcome and change it into a binary outcome, as someone had asked. Somebody was saying it, Samantha, was that Samantha? Okay. Yeah, so now we, just to remind ourselves how many classes there were as far as the outcome is concerned. And now we already did that, and we did that, and so here we have, right, so this is where I am going to now change the categories for the outcome, which is HD in this case, right? The outcome here. And so notice it's measured as an integer, which is not quite correct. We need it to be classified. So first I'm going to change all of the 2s, the 3s, and the 4s into 1s, so that there will be only 2 categories, essentially. There'll be 0s for people who don't have heart disease, and then there'll be 1s for all those who do have heart disease. So it's giving me some kind of message here about using loc and using the row indexer. But I try to avoid that because it is complicated code. Let me just make sure that that works. So I can add a new column here, and then I can look at my new my new, yeah, I see the import warning, Joanne. It's usually because I'm using an older method. It wants me to use look as my, okay, so let's take a look at our newly created column and see if that is what we want it to be. Okay. Yeah, so I had this as a different model before, and I tried to take out all the complex things for this session. Because one of my colleagues, Jelani, Lindsay, right? She told me, don't make it complicated, because she did that and she felt like, she just made it worse for the students. Yeah, this is usually set to ignore. Right, that's one of the best solutions to that, Joanne. Just set it to ignore all these warnings. Right, but you notice it did do what I wanted to do in spite of the warnings, right? Because it's converted my categories for heart disease into zeros and ones. So we have 0 people, 160 persons without any heart disease, and now we have 137 persons with heart disease. So we can actually take a look at that, and there are several ways. I mean, it looks like almost like an even distribution, which I'm surprised at by this, but we can probably do a plot and see how that's distributed. So here we have zeros for the women. Wait, what, is that correct? Because now it's saying the women have more heart disease than the men. And 1 for the men. I think that was what the data said. It didn't really say here, but I know on the Kaggle website, I think that's what it says, but I'm not sure. But anyway, so this gives us an idea of how the 2 categories are distributed, right? So this is something that we want to do. Now, like I said, we're doing a classification. Oh, right. So this is heart disease, not gender. Thank you so much, Alan. Right. That's why I'm confused. So this is a reflection of those who had heart disease and those who didn't, not male, female. So that's a different thing. So now we have, because male, female was already binary. I wouldn't need to convert that to a binary. So now so I want to, because these values here are an int 164, which is implying that it's numeric, and for classification, you need it to be, categorical. So that's what I want to do. I want to convert that entire column from a numeric column to a categorical column. So this is the code that you would use as type, and with this method as type, you can make all kinds of conversions. So if it is categorical, you can convert it to numeric, and if it's numeric float, you can convert it to int, and all kinds of stuff. And yeah, so sometimes there are other additional steps you have to make, but because I think this data set is for the most part, already clean, then we can go ahead and make that change. So here we changed our column from the int, where it was showing int. If you remember up here, it says int. So now we have changed it to a category. And now we can do a bunch of stuff, which is usually part of your exploratory data analysis, even though I have that labeled down there. It just kind of helps you to see what is going on. And I don't know why I did that several times, because I already knew what that. I think I just moved the code around unnecessarily. But here we have a nice plot that allows us. So count plot is one of those really handy methods in S, or which is short for seaborn, that gives you really nice visualizations of your categorical variable, right? Because a lot of times people focus on all the scatter plots with the continuous data and all that, but the categorical variables are where the data insight really lives, right? So here we have the gender, right? We have female, and then we have male. So we notice the two colors are blue and red, right? And one is for heart disease and the other, no heart disease, and one. So what insight can you gain from this, just this graph right here? Anyone type, you can type it in the chat. Yeah, absolutely. So you see how you can see that even before you generate any kind of model, right? You see clearly that when it comes to the ratio of heart disease. Oh, wait, somebody's saying more women. No, I think it's male. This is male, right? And of the male, these are the ones that have heart disease. And of the female, these are the ones that have heart disease. So clearly, as far as the balance or imbalance is concerned, more men in this data set at least have heart disease than those who don't. And for the women, you see that a lot less women have heart disease than those who don't. So yeah, so definitely gender is one of the features that is associated with the outcome. All right, so now once we've done that, we want to start building our model, but we can't just yet, because sometimes we have a large data set and we have all these features, and some people, they will just throw everything into the model and see what comes out, right? And if you do that, here's what happens, right? So you throw everything into the model, you get a model, gives you a certain accuracy or performance level, and then you think, oh, let me just tweak that some, and you keep improving, and you will get improvements, right? But is that the best model that you can build? Maybe not. So you want to be more strategic, right? So we want to make sure, first thing, that the features or variables that we include in our model actually have a statistical association with the outcome, right? Because if the variable has no association with the outcome, then it's not going to help your model at all. So in fact, it may even hurt your model. So one of the things we do is we generate the correlation matrix, right? And so what this does, it gives us a value for the correlation level between the pairs of variables, right? So of course we are interested in very specific ones, and because my heart disease here is now classified as a numeric variable, we cannot, it's not included, right? Because one thing about this method, it only will work on the numeric variables, but we can still probably do something. Let me see if this will work, right? Because the original data frame still has, yeah. So this is heart disease, right? And here we can get an idea of all the variables that are associated with that outcome, the outcome of heart disease, right? Because it's going, the correlation is between 0 and 1, or -1 to 1, right? If it's negative, means there's a negative correlation. And a lot of people make the error of thinking that if it's a negative correlation, then you get rid of it. No, sometimes the negative correlation can be very strong, and that can be very informative, right? In fact, in this data set, I think, well, no, I thought that the negative one was the strongest, but it's not. So we see Thal-Ac, which I am not sure what that meant again. So if we go back to our maximum heart rate achieved. Okay, so I guess it's under some kind of stress or activity, the highest heart rate that the person gets to, right? And that has a very strong negative correlation with the outcome, meaning as the heart rate measure goes up, the risk or the relative incidence of heart disease goes down. So there's a negative relationship. And that's the only one actually that has a negative relationship with the heart disease. So now in this case, in this data frame, it's still the, it's not the binary measure, right? We still have, I think 1, 2, 3, 4. So it changes. So the higher number, well, I don't know. They just classified it 4. It doesn't mean necessarily that 4 is like the worst case. It's just, they just use that. So I don't think it has any order to it. But so that's one of the things with the correlation matrix. You have to be careful about reading the correlation for values of categorical variables, right? It's because if it's not ordinal, then it's meaningless. But it does give you some idea of what is happening. So if we, that's a lot of numbers to read. So we can actually generate this wonderful heat map here. And, everybody loves a heat map. It's so beautiful. But what it is, it makes it easy to read, right? So if you just generated this, you would just see the colors and it would give you an indication of where the strong relationships are as far as, between the two variables. So here is our key, right? So the strong positive relationships, they have the lightest colors, and then the strong negative color relationships had the really dark, deep colors. So if we look here, this is our heart disease. Of course, it's strongly correlated to itself, so we ignore that. But if we look here at the values, right, we see that the strong negative correlation with that same phthalac again, and it's, of course, it's darkest, and then all the other positives, right? So those would be the lightest ones. So CP or chest pain, X-ang or something like, what's that? I'm not sure. Who knows what that is? I don't want to scroll back up again. Yeah, that's right. So we see here then that old peak definitely has a strong relation. In fact, it's the strongest, right? 0.5, that's like the highest value in all of these. So old peak and slope and X-ang and tau-ac, those are probably the values that are most strongly correlated with the outcome as far as heart disease is concerned. And so, this is kind of where you want to start. Oh, and we forgot chest pain up here. So those 5. Right, so those are the values that you probably would want to include in your model. So in my own research, I had all these values in there for different reasons. I had a very complicated tree, and I tried to kind of pare it down some to kind of make it easier to interpret. So if we generated a data set that kind of selected those ones that we think have the highest correlation, so this is my new data frame that I have now DF select, and I can take a look at that. This is the pair plot. This is another way to take a look at the relationship between mostly about the distribution of the variables, so in fact this one here is the tau-ac, and it's somewhat normally distributed, maybe. Clearly this is binary. It's not labeled as such. And then old peak here, and then slope, and finally heart disease, right? So this was for the, I selected from the one that I did not make the changes to. So maybe we can take a look at this. I don't know if I want to do that. Maybe I can do it else in another cell. So I can preserve this. So I go here and I do add a new cell, and then I do that. And if I wanted to select from the data frame that I had used to actually, make the heart disease a binary function as opposed to a, how many, 5 different categories, right? So now if I did that and took a look at it again, see, what did I do here? That was, we generated the pair plot. That's one of the things we learned. Oh, no, I didn't need to do that. Saving time from typing, you just copy and paste and make the minor changes that are required. So you do like this. Oh, I did not run this cell, so I have to run this first. Is that what I want to do? I'm not sure. So I'm selecting just these columns from the larger data frame, and hopefully that will, I think I messed up. The columns are probably not the same that I had lined up before, and so now it is giving me an error. Oh, I already selected. Oh, but why is this not doing a binary? Yeah, so this is a large part of programming. It is debugging your code when it does not work and trying to figure out what exactly you have done wrong, right? Because sometimes it could be a simple thing, as in this case, I think it was just the end bracket. All right, let's read the error message. When all else fails, read the error message. Categorical is not ordered for a pair plot. I know that. Okay, so I should know that. You can't essentially do a pair plot if the values are categorical. Yeah, you can do a correlation plot and you kind of get around that, but I guess it will not generate the pair plot for me. So we will just, let's see if we can do that. Although I think I already did this. Yeah, and then you can probably do the, it's late. What is the thing to get all the lovely pictures, the images? This, a heat map. Right, so we can get a heat map on our now the data frame that we have reduced. It's probably just, kind of redundant information, but it's just the things that you do, because if you made, changes to your data set, you want to always check and make sure that the changes that you made are the ones that you want, right? Because sometimes you can type something incorrect and the code will run and everything will go fine, but it may not necessarily have made the changes that you want, right? So yeah, we'll get rid of this right now. All right, so after you've done kind of selected all of that, there are some things I kind of left out in terms of doing all of the descriptive statistics on your model, generating the histogram for the age, and I probably could show that here, and I did not define that. So you do all this descriptive statistics because these are actually part of what allows you to tell the story of your data essentially. And if you know, when you have, you've given the task to build a model, you don't just go and show the model, right? You talk about the data, the quality of the data, the type of data, you build the context for your story, then you describe your exploratory analysis and all the insight that you've generated from that data set. And then you get to the model and you talk about how you built your model and the different steps that you used to generate the model that you have, and all of the challenges as well as the limitations that you incurred in building this model. And I don't know if I made changes to this. This is just looking at the distribution, right? And you know, certain of these values are normally distributed, others are not. And right, so this is where you get to the model building stage. So the first thing that you do is you have to separate your all of the features or the predicted variables or the independent variables from the outcome, from the dependent variable, right? So you'll have you know, essentially you're generating a formula where, I mean, in this case, it's not a linear regression, but it's still a mathematical formula that's involved. And so all of these features combined in a certain way are going to be used to predict some kind of outcome. So if you think about it in terms of the linear regression model, right, for a linear regression model, you would have an equation y is equal to ax plus bx plus cx, that kind of stuff. And it should be really x1 and x2 and x3 because they're not all the same x's, right? So these will be all the different features that are included in your data set, and there'll be some relationship between these features that when combined, you can make a prediction about the outcome. So this is essentially what we're doing. We're taking our data set that we have here, right? And what we're going to do, like this, we're going to separate all of these features. Let me see if I can annotate this. Yeah, so we're going to separate all of the x's from the y, or the outcome that we are trying to predict, right? So that's what we do when we Clay. Oh, sure. Yeah, so we have this code that we can use with our model building, right? So when we load in our modules, right? Remember at the top here, we loaded in a bunch of modules, including so NumPy, pandas, all of that is for the data set. The data frame helps us to manipulate the data frame and get it ready for the modeling. But sklearn, that is one of the more, you know, really popular type modules, and included in that package is the decision tree classifier that we're going to use. But also included is this train test split. So that is going to do the splitting for us. So we're doing two splittings, as it were. We're doing a vertical splitting of the data. So we're separating all the features from the outcome. But then we're also going to do a separation of the training. So we're going to separate the data now into train and test. So let me see if I can do is this drawing? No. right? So the first separation we do is kind of like this, and then we separate that, right? And then after that, then we do another separation where we kind of separate, our data into train and test. So this will be the training data. So train, oh my goodness, my handwriting is atrocious on this one. So this will be train, the train X as it were, and then we will reserve some of this to test our models once we've generated. And similarly, we're going to divide the outcome into the same ratio, and then this will be our Y train, and then we'll have our Y test. So those are some of the separations that we would do. We had imputed missing values. Would that come before or after the train and test splitting? So we try to prevent data leakage in the purest sense of the word. And so we separate our data before we make any kinds of changes or any kind of transformation, right? Especially if we are imputing missing values, say based on like a mean or something. Because if we use the whole data set and we use that to get the mean and we use that to impute the missing values, then we've actually used information from the test to kind of make the transformation, which then in that case, the test data will not be completely new to the model. So in the purest sense, in the strictest sense of the word, you want to do your separation before you make all your transformations. But there are stages to this, right? So there's the cleaning of the data in terms of some things that are just really you have to kind of take care of. And then there is some kind of exploratory kind of analysis. And even after that, there's a feature transformation and all kinds of different things you can do to your data. In some cases, people would have the train data, the validation data, and the test data. And it's a whole pump. So age is not predictive of heart disease, but gender may, or we cannot say this. Yeah, so in our data set, it appears that age is not a very strong predictor of heart disease. But you have to take that with a grain of salt. First of all, it's a very small data set, 303. Secondly, where you have to think about where this data came from. Is this from a hospital? Is it from the general public? Is it from a certain region? All of these things weigh in, right? Because in some data sets, age will be a very important indicator of heart disease, and in other data sets may not be. And it could just be that there might be an imbalance in the age in this data set. I'm not sure, but those are some of the things you want to think about. So this is the kind of the way we would divide our data set. I'm trying to get rid of this thing. Oh, that didn't work. There we go. Right. So that we can begin to put the data into our model and generate the data set. So here I am making that separation of the X into the Y, and I don't know what that is because I don't want to do it like that anymore. So after I selected, I did an even further selection. So I went from 5 to 3, and I don't know if I want to do that again because I think I messed up my model in the end, but let's see. So this is what that selection of the data frame would look like. being that the data set is so small, is the reason for not creating a valid. Yes, exactly. That's exactly right, Joanne. Yeah, because it is such a small data set. And, in this case, this is a model for demonstration purposes. If you were building a model that you were going to use for an app for the physicians, for their clinic, to make predictions, then one, you would get more data, and two, you would be more strict in terms of how you divided up the data. So this would be our X test, and now we would have our Y test. And so here is where we would use the train test split, right? And so the train test split, we would split the X into X train and X test. And we would also split the Y into Y train and Y test. The default is, I think, 20% test and 80% train. And you can change that depending on how you want. And you use this random state such that every time you ran this code, it would do the split the same way, right? So if you made some changes, you want to go back and you want to run it again, then the computer, the software would split it just exactly the same way that it was split before. So once you have made the split, then you're going to use the decision tree classification to create a model. You create an instance of this object, this classifier, CLF Genie. And then you use that Genie to fit the model based on your data, right? So your specific data that you have, now you want this classification tree to build a model that uses the data in your data set to make predictions about the outcome of heart disease, right? So you would run that, and it gives you some information about the model, how many leaves, and the random state in terms of what we set here, right? So we then, if we have this model and we wanted to say kind of create a function that would make predictions, so whatever. So now we have this model, like we have a formula, we have the like this is very much not this simple. It's a much more complicated model than this simple model here. But think of it in terms of this model. So now we have the model, we have Y, and we have some kind of values for the coefficient for each of the features. So what it is saying here, so now we have this model. If we know the values for X1, X2, X3, and in this case, it was the slope and the thal and the X and whatever those values. If we have a patient and we know that patient's measures for the slope in terms of their, I think it's their EKG or something, and we know their thal, AC, or heart rate something, and we know their exchange level, we can then use that to make a prediction, essentially, to classify them based on these features. And so now we have our model, we can create a function that we would then use to generate some predicted values. And this is just importing some more modules from the top here. And then, so I forgot to install all of this graph is at the beginning. So I don't know why I ran it, because it was already ran. So now we have, we essentially have our model. We can use it to then, make some predictions on certain values, and then we can compare the values that the model is predicting against the values that already exist, right? So we can take our test set now and we can use that to get some predicted values, and that would give us some measure of how well our model is performing. So in other words, if there are I don't know, in our test set, let's say there are 70 people who didn't have heart disease, and 30 did, right? So that's like a 30% heart disease rate. And so if we ran our model and it gave us something like, I don't know, 25 people had heart disease and 75 people did. So we can use that to then determine how accurate our model is and how well it's performing. And if that's a good measure, then we keep the model. If not, we keep optimizing it. In that case, we would probably want to go in and add some more of the features that I left out, So in the case of age, right, as someone was inquiring, we could include age in our model and see if that increases the accuracy, decreases the accuracy, or it has no effect on the performance of the model, right? So these are some of the predicted values. And here we see that our model essentially has a 73% accuracy in terms of predicting heart disease. So in 73% of the cases, it is making the right prediction, whether that is for heart disease or not. And so now we want to actually print out our tree, and I tried to simplify this. What did I do? And I didn't. It was, yeah. So failed to execute dot, make sure the graphs executables are on your system path. So I did download the graphs file, but for some reason, I cannot get it to work for me. And that is something I would have to play around with. Sometimes these notebooks can be a pain when it comes to loading all of these files. But essentially, so this was the model that I had generated, but I was trying to, make a much simpler version of this, and this is what would eventually come. But I made some changes in terms, I took out some features, and then I can't get the model to work. But I promise you that I will get this fixed before I send the file out to you, okay? So yeah, that's what you would do. Now I have a whole bunch of other stuff that I did in terms of, doing some more complex pruning. For example, with the, if I wanted to add some of the features and they were categorical variables, there are certain things that you can do in terms of, dummy coding or encoding with the one hot encoding. And so you take each of the category and you made it its own column. And you made some of those changes to, it's always about optimizing your model to get it up to the highest accuracy as possible, as well as still being generalizable to the general public, to a whole new data set that it has not seen before. But that is the general idea of how you would go about building your machine learning model. The decision tree, I think after linear regression, is probably one of the more easier models. There are others that are much more complicated. So they would require more feature engineering and, having all taking account of all the different metrics, not just the accuracy, because that's just one of the metrics that you can use to evaluate your model essentially. So yeah, so those are some of the steps that would be involved. Oh my goodness, it's almost 8:30. All right, anybody has any questions? Yes, Joanne, I think I may need to restart my kernel because I made so many changes to the data set right now, but I don't want to do that on camera. Yeah, that's part of programming in general, machine learning. Yeah, debugging your code is a big part of it. If you are not comfortable with that, then I would suggest that you get comfortable.
Agreed. Don't see any questions coming Yeah, definitely a lot to digest. So I'll send the recording out as soon as we get it up to YouTube. We'll get the recording out, and we'll also have uh, the actual notebook available.
Yes, I will send out the notebook tomorrow afternoon. I'll spend some time, kind of cleaning things up and making sure everything works, and I'll send it to you, and you can send it to everyone.
We do have
But any other questions? Which part of classification process is usually the most interpretation? Yeah, interpretation of the classification models, right? So the decision tree is the easiest, simple, right? It'll tell you straight. If your blood sugar is above this, you go this way. If your cholesterol is below that, you go this way, that kind of stuff. But the other classification models, like for example, logistic regression, you're gonna have, the true positives and the true negatives, and the false positive and the false negative, and you're gonna have to evaluate that in terms of what is important to you. So in in the case of a business, they might be more interested in the precision of the model, whereas if it's disease type prediction, they are more interested in the specificity of the model. So these are some of the things that you have to think about in terms of interpreting and optimizing your model, because you can go in several different ways. I went through similar exercise in the model pieces, went through a lot of trial and error coding, learning how to put everything together. It was interesting to see how the decision tree works in Python, and used to, oh, you used to R. I know, me too. I've done it in R several times. And so, yeah. sklearn is, I think, I don't know. I'm kind of biased because as a statistician by nature, R is hardcore, right? And you could do a lot more detailed statistics with R, but sklearn is, it's all the bells and whistles that that a data scientist love.
Someone asked, this is a good question before we head out. How did you get the slide part to work with the cells?
Oh, yeah. This is it's a extension of Jupyter Notebook. Jupyter Notebook has an NB extension. Let me see if I can pull it up here. Yes, so your Jupyter Notebook has all these extensions, and Rise is the one that allows you to convert your notebook to slides. And I mean, I think it's awesome. Of course, you have to make sure that your slides are prepared so that they run appropriately. But one of the best things about this is that you can actually create a blackboard. Oh my goodness, this is so awesome.
Nice.
Yeah, so that's one of the things I like.
Cool. All right. We are at time, so we'll have to end it there. Thank you so much to everyone joining. Thank you to our wonderful instructor. Ioana, thank you for a great presentation. Everyone seems pretty satisfied, so that's good. That's always good. So
yeah, I didn't get my treat, my nice treat to generate, but that's part of it. I'll get that out to you.
No problem. No worries. Everyone have a great night, and look out for the recording once I send it.
Yes.
All right. Take care.
Take care. Bye-bye.